So, hello everybody. Good afternoon for some, good evening for others. Well, I hope everybody is well, is healthy, taking care of yourself and the others. And continuing our seminars, today we have the pleasure to have Thomas Rometsch, I think something similar.
The second one was very good.
Okay, good. And he has a degree in physics and master degree in physics from Tübingen University with some stages in Michigan and Budapest. And now I think you are closing your PhD, the final closing.
I'm finishing my thesis, exactly.
Oh, that's great. And so today he is going to talk to us about survival of planet-induced vortices in 2D disks. So please, Thomas, the podium is yours.
Yeah, thanks for the kind introduction and for the opportunity to speak here. I'm going to present work that I did together with some colleagues here in Tübingen. First, Alex Siempras, he's a fellow PhD student. He now just moved to London to do his postdoc there. Then, of course, Willy Klei, I think he already talked in the seminar some time back, and also William Bethune, who's a postdoc here. And okay, let's just dive into that. So here's a little outline, three steps more or less. I'm going to first talk about the broad context of what we do here and some motivations for the specific topic. And then I'll describe somewhat our simulations, and then I'll move on to some numerical methods, how we detected certain things in these simulations. Okay. Let's start with the context. The context is here star and planet formation. The idea is to learn, right, to shine light on one little puzzle piece in this big puzzle of star and planet formation. And of course, we already have some quite good theory of how that all works. And oftentimes when I say I'm an astrophysicist, people ask me questions and use the opportunity, and then they say, how are planets formed? How are stars formed? And my best explanation in a nutshell is that stars are just balls of hot gas, and these balls collapse from a big cloud that leave some leftover material, and that's what planets are made of. That's the coarsest description of the story I can give. And of course, we can do a little better. This is now one of the many sketches of star formation showing the different stages in the process. And I just took this from, I think it's the American Association for the Advancement of Science here. And it tells us the approximate timing and the approximate scale of the process here. So we obviously star formation starts in a molecular cloud. A part of it is prone to gravitational collapse. Then over some 100,000 years, there's the first and the second core is formed. And then we get the protostar, essentially. And length scale for that is 10,000 AUs approximately. And as we go on in time, it moves from almost spherical collapse to some structured accretion through a thick disk and the ejection of material through jets. And before it was just the big envelope that just moved in radially. Now we have some substructure. And when most of the mass is accreted, we have a disk left over as a consequence of angular momentum conservation, right? Most stuff just rotates slightly. If you just have shear motion in the molecular cloud, you have rotation and angular momentum with respect to the central point of the collapse. And as a consequence, we have a disk. Now, along the angular momentum vector, material can just collapse. So we naturally end up with a flat structure. And we have flat structures in the universe everywhere. Protoplanetary disks to galaxy disks. disks everywhere. And after some point, right, jets die because there's not enough energy fed into the central regions, and angular momentum is transported away, and also the disk disappears after some time. And that's typically up to 10 million years, how long these disks live around the young stars, and we call them protoplanetary disks. And all that material here is mostly gas, so hydrogen and helium, and percent is solids, and we call it dust. So the ISM, the interstellar medium, has 1% dust approximately, and that's what rocky things like our Earth is built out of. And then the story of planetary system formation goes on, and there's dynamical interaction between the planets. Okay. What we'll focus on here is somewhere in between D and E, so a couple of million years old. And in this sketch, I like that there are already planets embedded here. And you see these gaps. So, well, the takeaway message from this talk, if you didn't know already, if you have a big planet in one of these gaps, they open if you have a big planet in one of these disks, they open a big gap. As you know, also from example of the rings of Saturn, you have the moons, and they push away the material in their vicinity. Okay, so we'll go in between D and E and look a little bit what happens there. As you undoubtedly know, our planetary system, our solar system, is not the only one out there, and there, on average, I think there's one planet around each star. And it started in 1995 with radial velocity measurements, and now we know many, many, many planets. And here, this is taken from NASA, this sketch. We have a diagram of planets found. These are the data points in diagram orbital period in days versus relative size to the Earth. Now, this can be radius of the planet, mass of the planet, the axis a little bit scaled, of course, but the general overview is the same. And we have lava worlds here, we have rocky planets, ocean worlds. Right? The further you go away, the cooler it gets. So we have hot Jupiters close to the star and cold gas giants, or cold Jupiters far away from the star. And my colleague Tobias Moldenhauer talked also at some point about the atmospheres of Neptune-sized planets, more or less, or Earth-sized planets, how recycling happens there. That's more or less in the ocean worlds or rocky planet regime. And today we'll deal with planets up here in the cold gas giant regime. So big planets, relatively far away from the star. Relatively far away means 5 to several tens or 100 of AU. And this was more or less the picture we had. I mean, Kepler came and we saw lots of planets. Radial velocity measurements allowed us to find these cold gas giants. And we had some images using Hubble, for example, of disks, but they were quite blurry. And then ALMA came along. And at least since 2015, we can make nice images of these disks. So ALMA is a radio telescope array in the Atacama Desert. And you have there about 50, 60 telescopes, radio telescopes, and you can interfere the signals there. And as the Earth rotates, you can cover essentially all the UV coverage space, and that's the Fourier transformation of an image. So you observe with these radio telescopes, and you Fourier transform, and you get images like this. This is taken from the D-Sharp survey, that's from 2018. And they aimed at big and bright disks. And what we see here are the targets of that. A number of disks, and in every disk you see substructure, or in almost every disk you see substructure. And there have been many observations since, and substructure is in many of the disks observed. Some are quite smooth, but most have substructure. And the first part of my PhD was indeed to study how accretion happens through these disks with gaps. So you can actually accrete material over such a planetary gap. But now here for this talk, we'll zoom in a little to HD 143006. All these disks have nice telephone book names. And here you see this azimuthal asymmetry. Also here in this disk, there's some azimuthal asymmetry. Some disks have spirals, but we're interested in these blobs now. Okay. And it turns out this asymmetries in the structure, of course, you need to explain them, right? These disks are quite, you could assume they're axisymmetrically symmetric, right? Because they nicely rotate. So how do you form these big clumps of matter, essentially? Well, we see clumping of intensity in the observations, but then we infer that there's also a clump of matter. And it started with van der Marel et al. 2013. You see that images were much coarser then. We didn't have that fine resolution. And you already see that there is some clumping of millimeter dust. These are radio telescope images also. There's some clumping of millimeter dust at one specific location in the disk. And we also have micrometer dust data. So the nice thing about radio astronomy is that we have essentially spectra over the wavelength region where we can probe different dust sizes. So we see that in one dust size, there's this clump, and this was interpreted as a vortex. We'll come to that, what it means if you're not familiar with it. And also here in this particular disk, Jane Bay et al. In 2016. Now the bottom is an ALMA observation. This also clumps at one side. And this is a sphere image. Sphere is also quite nice. It's at the VLT, also an interferometric instrument, but you can probe much smaller wavelength. And also here in different wavelength bands, probing different structures in the disk. So a sphere probes the surface of the disk. There we also see this big asymmetries. And also now this is from D-Sharp. D-Sharp were a big study with 10 papers. This was one paper dedicated to this disk here and the asymmetries. And you see also there, we see this asymmetry in different wavelength bands. So this seems to be a persistent structure that's really there. And people having simulated disks before, they immediately jumped to one hypothesis, which is that these things are vortices. So vortices kind of swirly motion, and in these disks, they attract matter, so they accumulate matter. And how do we know that? Here is some snapshot of a simulation I did. Here we have a top-down view on the disk, and these are the orbits of two planets. This is a two-planet simulation here, two massive planets. When they interact, they excite vortices easily. Then we have here this accumulation of mass. And if you run a simulation, how this would look in ALMA, this is how it looks like. So if you compare this image on the right to, say, this image also with ALMA, well, there's quite some resemblance. And to show you that how vortex would then look like, now I show some streamlines, and here on the left you see the region the right plot covers, and the white lines are the streamlines with arrows. And I put on this arrow here, there's this kind of motion in the disk. So if you were to transform into a local frame here, the matter really swirls around. Of course, the whole disk is still dominated by the Keplerian motion around the star. Okay, so this brings me to the, this always the introduction to why we want to study these planet-induced vortices. They're often invoked to explain observations, or at least in some instances, and we know them from planet disk simulations. Now, in this study I'm presenting here, we explored the role of radiative effects on vortex lifetime and how they appear in hydrodynamic simulations. So we do simulations and we look how long the vortices live. This was already done for a couple of other parameters before, namely viscosity or self-gravity. Both if you have high viscosity, you tend to smear out these vortices, so they die faster, or they don't form at all. And self-gravity also seems to inhibit formation of large vortices and kind of stretches them apart, so they die early. And the following is written up in a paper that's accepted to ANA that should come out next month, but it's already on archive. If you want to find it, just go on ADS and search Rometsch as the first author. There are, I think, 5 papers. There are not many other people, not many other scientists with the name Rometsch, so it's easy to find it. Okay, so now that for motivation, let's go a little bit into what we actually simulated. So we have 2D disk model, these protoplanetary disks. They are mainly gas, so we simulate the gas content. And we make the approximation that we can simulate them in 2D. We vertically integrate the hydrodynamic quantities. Speak to that a little more. We put in a Jupiter mass planet, and as we put in the planet, we create a vortex, or vortex is formed in the simulation. You'll see a video later where you can see that live. We prescribe some initial conditions. Obviously, we need to do that. We also have boundary conditions. They will come on a later slide. And we employ the alpha viscosity model. Now, these protoplanetary disks are accretion disks, meaning they transport mass from the outside in, which needs a process that transports angular momentum from the inside out, right? Angular momentum is conserved. That's why planets stay on the orbit. Same would happen to gas if it had no way of exchanging angular momentum with the surroundings. And one way of exchanging angular momentum with your surroundings, if you're a gas particle or a gas parcel moving in that disk, is via viscosity. So the viscous stress tensor actually allows for angular momentum transport. And this alpha viscosity is a parameterization of turbulent viscosity. If you do the numbers, then molecular viscosity of hydrogen and helium is at least 10 orders of magnitude too low. But if you look what turbulence in the disk does, this gives rise to some effective viscosity, so to speak, sometimes called turbulent viscosity. There's a paper from 1972 by Shakura and Sonyaev, which most people refer to, and this has become more or less the standard way of simulating it. But it's very coarse, and alpha, we take it here as constant throughout the disk. In reality, it will change through the disk. So obviously an approximation here. And then to handle radiative effects, we employ something called beta cooling sometimes. So the idea here is the temperature in the disk is more or less set by the irradiation from the star and the radiation from the disk away into space. And this can be approximated by having an exponential decay back to this. So whatever happens in the disk, it decays back exponentially to a background temperature. And the time scale for that is given by tau relax here. And this depends on the beta parameter and the orbital timescale. So that's why it's called beta cooling. But if you cool too much, it can be actually heating. So beta relaxation or thermal relaxation is another word for that. Okay. And what we actually do is we solve the Navier-Stokes equations on the grid. Now, just refresh your memory on what the Navier-Stokes equations are and tell a little bit here. So first equation is conservation of mass. So the left side here with the derivatives just tells us essentially how the flow of gas changes in time and space. How that is connected, the time evolution to space, to the spatial derivatives. And then for conservation of mass, or here this is the density. So as you compress, the fluid density changes. That's the right side here. That just tells us mass is conserved. We also have conservation of momentum. That's the second ingredient to fluid dynamics. And left side, again, tells us how time and space derivatives are connected, how the flow moves along. Then flow is subject to pressure, can't compress, and here gravity denoted by G. We have a planet in there, and the planetary gravitational potential is put into this G. And also the viscous stress tensor, that's where the alpha goes into. Then also energy conservation. Again, left side is what the flow does, and here we have some compressional heating. We take account of that. We have some viscous heating, so via viscosity you can dissipate energy into heat. And then we have this Q relax, which was the beta cooling, which cools back to the polar profile. Okay, so we solve these equations we discretize them on a grid, and then we solve the equations using the Fargo code and the Pluto code. So in the study we use two separate numerical codes. This is beneficial in many situations, I think, because we have though both are grid codes. One is a finite difference code, and one is a finite volume code based on a Riemann solver. So different numerical schemes. And I would argue that using two different schemes gives you more reliable results than only one scheme. And this grid is log space in R, so finely resolved in the inner parts, and the outer part that also has good properties for the simulations. Then we span some radial domain, have a solar mass star, Jupiter mass planet in there. We have different viscosities, different typical viscosities of the range where they are thought to be. So the lower viscosity, the easier vortices can form. And then different values for the cooling time scale and a aspect ratio. So the disk is quite thin, and the ratio between the pressure scale height and the radius is called the aspect ratio, and that's 5% here, so it's rather thin. That's also the argument why we're allowed to do 2D simulations. And we have some boundary prescriptions where we damp waves that we don't get standing waves, because we have reflective boundaries to not have all of the gas disappear through the boundaries, essentially. And sometimes we employ self-gravity. Okay. Now, for all this to make sense, right, for all the later results I show you to make sense with the vortices, I just want to make sure that that I introduce the basic concepts here. Like I said, vortices are things that swirl around. And if you have here an R phi plot of streamlines, right? This is from a more or less theoretical paper where they plotted the streamlines of a vortex solution. So vortices are the solution to the Euler equations or to the Navier-Stokes equations also. And what you can see, these are streamlines, and flow. There's a flow just along these ellipses here. These are streamlines. So there's a vortex core, which is really separated from a separatrix, the blue one, from the outside, if there's no viscosity. If there's viscosity, of course, they can intermingle. And the typical quantity to characterize swirling motions and vortices and fluids is the so-called vorticity. And that's just the curl of the velocity. And in our situation here, where we're in a 2D disk, we take the vertical component of this curl here. And that just tells us how much it swirls around. So, and the disk has a background vorticity, but on top of that, there's additional vorticity from vortices. Another quantity that's used to identify vortices, and where we can also say something about analytically, is the so-called vortensity. It's different names, sometimes also potential vorticity, that we just divide by the surface density. So the surface density is the vertically integrated density. And vortices nicely pop out here, because the vorticity contribution from the typical vortex here in our study is negative. So it goes from the background state, which is positive, to more negative values. So it lowers. And then vortices also accumulate mass. They essentially have a Gaussian profile. So for some range of the spectrum or of values which is relevant here, first, because of the vortex, the vorticity declines. And then also, if you divide by density, it gets even smaller. Well, until we reach 0, and then it changes, it gets bigger again. But this is a good tracer for vortices. And we can even write down the evolution equation for this vortensity. So again, here, this is how it changes in the flow. And essentially, this depends on the baroclinic term, so the curl of gradients of sigma and p. If p only depends on sigma, this term goes away. So then it's conserved. And there's some viscous term, which just spreads everything. So this dissipates also vorticity. So we can destroy vortices with that, and we'll see that. Okay, so in the study, you saw it earlier, we had a couple of parameters, right? The alpha parameters, the beta parameter, that's 3 times 2, that's 12 parameters. Then we have 2 codes, that makes 24. Simulations at least to check these. Then we did it with 2 codes, that's 48. And as you probably know, if you did simulations yourself, you don't just do the simulations that appear in the paper, but you do 4 or 5 times that. So easily 100 simulations. And that's what we actually had. We had 130 simulations, I think, run on our local HPC cluster. But now the, the tricky part comes. We want to know the vortex properties of in these simulations for every snapshot we save. So we save 500 snapshots per simulation, and then we want to check which vortices they are. And that's like of the order of 1 million snapshots. And you could go in and trace all these vortices yourself, but that would take weeks in time. I estimated it to be 9 weeks, I think, just in work time. Well, that takes too long, obviously, and if you make a mistake, you have to do it again. And then we would also like to have numerical properties of that. How massive is the vortex? How high is the density? How low is the vorticity? And so on. How large are they? So here, what I developed is a detection algorithm using some computer vision algorithms. And the result of that is a cool tool called Vortector. It comes from vortex detector. Sounds a little bit like a superhero, which is, of course, no coincidence. And it's available on GitHub. And what I'll show you now is the output of this detection routine. Right? On the left, you see the vortensity, so how much it swirls and exaggerated by density that's there. And you immediately see something popping out here, very bright. What you see here is an R phi plot, so radius versus azimuth. And we start at the planet location, so we look outside of the planet. That's where the vortices form, which we want to look at. And on the left, you see vortensity. On the right, you see surface density. So you see the planet created a gap. That's why it's dark here. Then there are spiral arms launched by the planet. And there's this big mass enhancement here. That's actually a factor of 5 larger, I think, compared to the initial values. So that's how a vortex looks like, a big vortex looks like in one of these disk simulations. And we can see here, this vortex actually launches spiral arms by itself. That's quite typical. That's just because of the density waves launched by this perturbation. So planets and vortices launch spiral arms here. And now, here on the left, you can already see this vortex region is nicely, has these nice, more or less elliptical iso surface lines in vortensity. So the lines are iso value lines. So the basic idea of this algorithm is here to look for large elliptical lines in here and then fit some quantities. Okay. So now if I go back and flash back again, this white contour appeared. Here, that's the largest contour that satisfies some conditions. It's more or less elliptical, doesn't deviate too much from an ellipse. And here in the density plot, we see the same region. And the idea is to now take this as a vortex candidate in the snapshot, and then to fit some quantities to it. To both, we fit a Gaussian function. And for the density, this fits remarkably well. And actually, there are some analytical solutions, vortex solutions to the hydro equations. And if you go through them, you see that actually vortices, the exact solution predicts a Gaussian density distribution. So that's no coincidence that it works here. And now this is quite a proper vortex. It's quite large. Okay, here the enhancement over the background density is number of 3. And just to give you an estimation for the parameters we used here for the disk surface density, the gas enclosed in this region is of the order of a Jupiter mass. So it's a lot of mass here. And I talked a little bit about this identification process. And here's also a snapshot. If you look at the left side, there's this thick black line. That's the initial isodensity line, isovortensity lines. So if I go back, we take this box here, the iso value lines, we put them into the black box. Then we mirror the lower side up here and the upper side down here. If the vortex were to sit on the boundary, we really need that, otherwise we wouldn't see it. So we do the identification on both things, and here the red one is the largest, more or less elliptical contour. You see it here on the right. Then we fit an ellipse to that, the orange ellipse. And then the blue area is the deviation from the elliptical shape. And if this blue area gets too large, we throw it away. Everything that fits, we consider as a candidate. And the identification here on a typical grid of 1 million grid cells runs about 100 milliseconds. That needed some optimization, down from 10 seconds to 100 milliseconds. But nonetheless, we can now apply this to 1 million snapshots if we have access to a compute cluster, of course. And the resulting data we get, now you'll see an animation of one simulation. Again, the same. On the left, it's vortensity. On the right, it's surface density. And you will see how the planet shapes the disk. It will create a gap, and then a vortex will form. Actually, several small vortices will form that then merge together into one large vortex. And now you see this evolve quite nicely, and at every point in time, we really have information about the vortex here in the simulation, and we can track how it migrates outward here a little bit. And we can track how it changes mass, how it changes size. And essentially, we can track all its lifespan. And that's the important part here. Okay. This goes on for quite some time. This particular vortex is very stable, and it migrates outwards, so it's quite neat also. Now, I should have mentioned these panels on top and to the right are slices through the vortex. So that's a radial slice through the vortex. It's an azimuthal slice. Okay. And now, as we have all this data, we can also plot this data as the mass of the vortex here. It rises in the beginning and then slowly declines. You can also plot the position, it moves out, because the gap, the gap created by the planet, actually widens over time, and that's traced here also by the vortex. So the vortex is created when the gap is not even finished. And we can also, the shaded area here gives the size. We can also track that. Due to the detection algorithm, the way it works, at some point it just dissipates. So it doesn't go down to 0, but rather there's a limit on how much the vortex has to spin, so a limit on vortensity. That's why it disappears at some point. And also here on the bottom panel, that's the minimum vorticity in the minimum vortensity, so our vortex quantity inside of the vortex. And you see here it drops down, and then it evolves for some time, and then it goes back to 1, which is the background disk. It's normalized by the background value. So we can use this lower panel here to track the evolution of the vortex. And obviously now if you take here this time, right, where it goes back to 1, or almost where it goes back to 1, minus the time where it formed, we have the lifetime of the vortex. And now we did this for 48 simulations, I think, at 2 different resolutions. And I'll now show you an overview plot of all the parameters for 2 different resolutions, and we can see some amazing things there. Okay, so on the left side, you see the results for an 8 cells per scale height simulation, on the right side for a 16 cells per scale height simulation. Cells per scale height is just, I told you before about the aspect ratio, right? About the disk scale height versus the radius. Now the scale height, this CPS number tells us how many cells are in the scale height. And 8 is a rough estimate. 16 is double of that. That's much better here, as it turns out. But keep in mind that if you increase the linear resolution by a factor of 2, your total resolution increases by a factor of 4. And because the cells get smaller, we need to use smaller time steps to track the fluid. So the computational cost on the right side for 16 CPS is 8 times the one of 8 CPS. So here we very easily run into runtime constraints, because these simulations here took weeks to months to simulate. Now what we can see here on the horizontal axis, it's the beta parameter, so how fast the disk cools. It cools, or it changes back to its background state very fast on the left side, almost as if the temperature was fixed. There's also an approximation often done that the temperature is just fixed. But here we cool back very fast. On the right side, it cools very slowly. That's more or less an adiabatic regime where the gas is just left on its own. So compressional heating becomes, for example, very important. Here, the gas just can't get rid of heat through its surface, for example. Now, for 8 CPS, we get a little bit of this V shape here. You see that these are just connected for visibility, not because of physical reasons. Now, for high viscosities, alpha 10 to minus 3, almost no vortices form. That's what we know. You can't really form a vortex in honey, whereas you can easily form it in your vortex in your coffee by stirring around. And as we decrease viscosity, the vortices live longer, for some 1,000 orbits nearly. And if we even go further down, they go up to 2,000 to 3,000 orbits. And for this beta of 1, we have a minimum. That was quite surprising and very unexpected, actually. We expected to have a monotonic decline here. And here's a big discrepancy between our codes at this lower resolution, and we couldn't find out why, actually. But as we move to higher resolution, this discrepancy disappears, luckily. So we attribute it to too low resolution. And here we have another regime where actually the vortices live for 10,000 and more orbits for very low viscosity. And the fact that 10 to the minus 5 and 10 to the minus 6 are so close together indicates that the numerical viscosity in our code, so every grid-based code, every discretized code has some inherent viscosity, so inherent diffusion, essentially. And in our case now, this becomes of the order of our physical viscosity. So we really test the limits of our code here. But this numerical viscosity goes down as you increase resolution. The finer you resolve it, the smaller is numerical diffusion. We see the same trend here with viscosity, but this new long-lived regime here pops out. And this tells us that really the the radiative processes in these disks are very important for the lifetime of these vortices, which in turn, of course, is important for the interpretation of observations. I'll come to that in a second. Okay, so takeaway message, just by changing the time scale on which the disk cools, you get drastically different behavior. You get short and long-lived regimes for these vortices. This was not really known before. And of course, now you can ask how long is the time scale at which position in the disk, and this will help us to interpret the observations. And now I showed you this evolution equation of vorticity before, and we have this first term here. And since our pressure does not only depend on density, but also on the sound speed, which depends on temperature, this term plays a role. And here you can see the distribution of this term. That's radius, that's azimuth, and you see this, and the vortices here are marked with a green line. You really see this dipole structure here. That's what you expect just from estimating that analytically. But you also see that the planetary spiral arms really have a big influence here. And here this structure becomes very messy. And in some sense, you can think about the change of vorticity or the decay of vortices that's given by the integrated value of this over time. So as the vortex moves around in the disk, you have to integrate these values, and then you know how your vorticity changes. And that's quite messy. And we couldn't find any pattern in here that would give us indications as to why these two different regimes we saw before, here these two regimes, long-lived and short-lived, why these form. But it seems there's something hidden in there which we couldn't disentangle in this project. Okay, so just let me summarize these results. Vortex lifetime here in these protoplanetary disks for vortices that are launched by planets depends on radiative processes. They're very important. We have one short-lived regime where we have 100 to 1,000 orbits. This is the case for beta being larger than 1, and that's associated with the inner parts of the disk, so the inner few AU. So there A, the orbital timescale is short, and B, the lifetime is short. So we shouldn't really observe them, right? Would be an observation of chance if we captured one of these. And then there's the long-lived regime, tenth of thousands of orbits, or 10,000 plus orbits at beta of 0.05. So then the timescale is very fast on which it cools as compared to the orbital timescale. Of course, that makes sense. If you're further out, your orbit is longer. So if you cool on the same timescale, even as further in, this ratio is much shorter. And this is the case for R equals 50 AU, and that's where we find these big asymmetries, by the way. And if you run the numbers here for a time scale, that's easily 10 million years of vortex lifetime. So that's on the order of the disk lifetime. So then it's not so much of a chance observation anymore, because we really sample then the whole population. So this suggests that we really can observe these vortices out at these large distances, and that's the preferred location for the observations we would expect it. And here just some ideas for future improvements of such an undertaking as we did it here. 3D simulations, or the 3D structure of these vortices, is also important. These vortices are not only decayed by viscosity, but they are different. They're unstable to some configurations. Namely, the most important is the elliptical instability, but we really need 3D structure for that. And for the whole regime here of vortices, they're susceptible to this elliptical instabilities. But these simulations take months to years. I ran one at the lower resolution here, right? You add an extra dimension. I ran one of the 3D simulations, and this lived even longer as compared to the corresponding 2D simulation. So there's even more at play, but 3D effects are certainly important. Then it would be good to treat the radiation more properly with proper radiative transport. And then it would also be good to include dust particles, because what we see in the observation really is dust. We can't trace the gas because the gas doesn't have any rotational lines which we can pick up with ALMA, for example, in the temperature ranges we have in the disks. Okay. So now let me quickly go over the implications for what does this mean for exoplanet research, this little puzzle piece we shed some light on here. This is important for interpreting the observations. Right? If you see asymmetries on the very inner part of the disk, and someone claims, hey, it's a vortex, we can say, are you sure? Let's try to check that. If we see it on the outside, we can do the same thing. But I think this finding here underlines the argument that these asymmetries might really be vortices. Then what I learned during this project, there are really still many uncertainties in our modeling parameters. So I talked a little bit about turbulence, about the turbulent viscosity, but also the beta parameter. We need to do further modeling there of the microphysics. These are only two things where we still have large uncertainties on our modeling parameters. And what's interesting also here in the study is that we really tested the low end, or that our physical viscosity got on the order of our numerical viscosity. So we pushed our codes really hard. And this also underlines the importance of doing proper resolution tests if you use hydro codes, right? You can't just use one resolution, find something, but you really test higher resolutions. Good way is also to test lower resolutions and see if the same thing still appears. It's also an indication. Okay, so with this, I thank you very much for your attention. It was nice to be able to present this project here. And now I'm happy to take questions, and I'll do my very best to answer them.
Okay, Thomas. Thank you very much. Very, very clear presentation. We are open to questions, so anybody would like to make a question, feel free to do that. Well, I have one in this last slide you are showing here. You said applications for exoplanetary research. I was wondering, let's say something more simple. What the vortices contribute for the evolution of the disk in terms of planet formation?
Oh,
does it help? Just
very good point.
Induce, what's the main effect of the
so we saw, right? We saw this. Let me quickly jump back here. But we have this peak in density. That means we also have a peak in pressure. And that means we can accumulate dust particles. So the moment we have a vortex, we can efficiently concentrate dust particles to form rocky stuff. So that really helps. Of course, here, right, we introduced the vortex with a planet. So that doesn't help us to start planet formation, but as soon as you have these vortices, you can efficiently form planets via some routes. But these vortices can also be formed by other mechanisms in the disks. So it doesn't need to be a giant planet. It can also form spontaneously via an instability. So this is really one route to form cores of giant planets or more rocky planets. So in this respect, these vortices might play a vital role. They're one route to rocky objects.
I see. So they would accumulate dust and help us accelerate the process.
Exactly, yes.
No, that's good. Okay. So, Ricardo, please.
Hi, Elton. Thank you. Thank you, Thomas, for the presentation. My question is kind of similar to the audience. It's like when you detect those vortices on disks, can you have any information about the disks about the disk giving those vortices? Like if you detect a vortex in a disk, I mean, can you say something about the disk?
So you mean whether we can infer disk parameters from vortices, something like that?
Yeah.
I think direct inference doesn't work. Therefore, the model or the parameters of these disks are too uncertain, right? Unfortunately, we just can't go like the reverse simulation. That would be very nice. Of course, we can do things like parameter studies and then make some educated guesses on the parameters in these disks. And I think vortices can really inform some decisions there, because we really see them in observations. They're an asymmetry in the right, and the asymmetry can give us additional information. It's not just smooth background. There really is something, and that in some sense rules out some parameters for these specific disks. And of course, they're a hint that planets are there, and then you have to really look at the structure. And right now, it's amazing, an amazing time, because there's new data and really fine data. Right, Richard Teague, for example, pioneered the study of the dynamics in the disk. So from these ALMA observations, you can even extract how the gas moves at different heights in the disk. That's quite amazing. So I think we can use these vortices or the asymmetries, all asymmetries, to make some informed guesses. But I'm afraid there's no direct route. I would really like that, but not yet.
Yeah, I was talking more like your last the last part of your answer. Like if you see a vortex in a disk, you could try to infer that there's a planet forming, or at least dust coagulating, or something like that.
Yeah.
And my other question is like you talk about 3D simulations, but you also found some regimes in your 2D simulations. Do you expect those regimes to change a little bit, like the short-lived and the long-lived regime with 3D simulations, or you have to run the simulations to see that?
Well, yes to the second question. I expect. What's my expectation then? I expect this two regimes to pop up nonetheless. I suspect the radiative effects are also very important there. But since there's another instability, the elliptical instability coming into play, I'm not sure, of course. So what this 3D simulations is, of course, the natural continuation of that. And now that we probe the 2D space, the 2D simulation space or parameter space, we can now make an informed decision on which 3D simulation to run, which will be maybe 5 simulations, of course. So, yeah. So answer is, I hope it stays the same. That would be nice, obviously, for this paper, but we have to see.
Yeah, I was asking because your results depends on the beta parameter, which is a parameter that is not very well constrained, as far as I understood. Yep. So I was thinking more like if you have 3D simulations, maybe this dependence change or at least varies a little bit.
Mm-hmm. Yeah, 3D would be quite good, but then the proper way to do it, right, including radiative transport through the vertical direction in the disk, that's still too costly. I couldn't run that. So also for the 3D simulation, I have to use this beta prescription. Otherwise, it's too costly. That would be 2 to 3 years at least.
Well, thank you, Thomas. Thank you for the presentation.
Yes, glad to do it.
Okay, thanks, Ricardo. I have another one. It's also more similar to what Ricardo asked. When you take into account, you didn't do it yet, it's planned for future, but when you take into account the grains, what's the main aspect that in the dynamics of the gas? How does it affect it? I mean, for the turbulence for this
So
spiral?
usually the way we think about dust content in the disk, we call it dust to gas ratio, right? How much dust in mass you have versus gas. And if you start from the interstellar medium, that's 1%. But in these vortices, indeed, you can get up to 1 or even higher. And then dust feedback from the feedback from the dust onto the gas, in this case, then also gravitationally, overcomes some restrictions, right? And then it can be a runaway process even, and that's indeed one way to form solid particles in these vortices by accumulating them first, and then you trigger gravitation collapse, and boom, you have a solid particle. And that overcomes things like the drift barrier, like the fragmentation barrier. That's quite a nice way. There was also the proposition, there was a paper lately on how to form vortices just in a smooth disk by viscosity transitions. That's also quite nice. So vortices caught my attention quite nicely. They're very interesting objects, and they're quite amazing. Vortices are also the building block of turbulence, and we can describe that statistically, but we don't understand it. So there's lots and lots of opportunities for research here, I think.
Yeah, but the beginning, I think, is the gas that will produce the initial vortice. Then the process may be accelerated by the dust, but the gas that makes it, it's not the dust that would generate initiate the.
So you need an instability in the gas motion, with which you can create vortices. Then you can accumulate dust.
No, to create vortices.
Yeah.
Okay, good. Thank you. Anybody else? Any further comment or question? Okay, so I think that's it. Thanks very much, Thomas. I think it was very nice to hear you.
Okay. Shall I stop sharing? Then we can
please
proceed to the discussion.